So last time we took a look at electric power, essentially what kind of power is running through a circuit based on either current and voltage or voltage and resistance or current and resistance. We went through different ways of actually solving for electrical power if we're only given two out of those three things. So just kind of go through Ohm's law quickly. Really, we can look at it as current is equal to voltage over resistance. That's one I like. So for this very, very simple circuit here, 12 volt, let's say I got a 12 volt battery hooked up there and I've got a 3 ohm resistor on it. If I want to know the current running through it, it's voltage, 12 volts, divided by the resistance, 3 ohms. All right. So 12 divided by 3 is 4, and we should know that current is measured in amps. All right, so that's Ohm's law. That's very basic, simple circuit. We know, however, that most circuits probably not that simple. Let me make that one a little bit closer. So let's say we still have a 12 volt voltage source, electromotive force supplier there. And this time, we're going to have 3 resistors hooked up. All right, so in this case, I've got 3 resistors, and let's say that they have resistances of 2 ohms, 3 ohms, and 4 ohms, all right? All of these are connected in the same loop, essentially. They're all in the same series. So this is a series circuit here. All 3 things are right in a row. You know, the series is this resistor, then this resistor, then this resistor. You know, that's the path like an electron would take to go from essentially the negative end through to the positive end, or the electricity goes from the positive end to the negative end. So now the question should be, you know, how do I apply Ohm's law, I equals V over R, to this? You know, I've got 3 different sources of resistance. Really what I should see here is my voltage source, you know, that I'm supplying here is really driving a current through the wire. With series circuits, the thing that you have to remember is the current going through this resistor is the same current going through this resistor. For series circuits, the current is the same for all resistors, okay? So for all R's, okay? The current is the same. To figure out to use Ohm's law here, I know I'm stumbling a little bit, okay? The current's going to be the same for all of them. So in order to actually figure out what that current is, I need to figure out, well, how do I figure out the resistance here? And for series circuits, this is really, really easy. Essentially, what we're going to look at is we're looking at the equivalent resistance is just going to be equal to the sum of all of the resistances, okay? And it doesn't matter how many resistors you have in series, you're just going to add them together. All right, so in this case, so really the big kind of takeaways here, the things that you're going to need to remember is this stuff right there. Like if I were to write stuff down on a note card, like this would be it, okay? So if I want to know the equivalent resistance for this circuit here, I've got 2 ohms plus 3 ohms. This is going to be some very, very basic math, plus 4 ohms. I'm not even going to get out a calculator for this. 2 plus 3 is 5, plus 4 is 9 ohms, all right? So in this case, what I can do is I can essentially take these 3 resistors and I'm going to treat them like they're all together in one resistor, okay? So I've still got a 12 volt battery, and now I just have a 9 ohm resistor on it. And now my math becomes pretty easy, okay? So now I can actually use Ohm's law, I equals V over R. So I is equal to V, 12 volts, over the resistance 9 ohms. Let's see, and that should be equal to 1.33 amps. I'm going to need a calculator here anyway. Let's double check that. So I've got 12 divided by 9 equal 1.33. All right, good enough. That's close enough for me. You know, I'm not a big sig fig fan. So that's the current going through this wire. So I'm even just going to pop that. That means that's the current going through each of these 3 resistors here. And it's important to know. What we're going to see though is as that current moves through each of the resistors, there's going to be a voltage drop off. So if I just kind of scroll down here, 2, 3, and 4, right? So I'm going to draw this out maybe a little bit bigger. And this way I have some room to put some things in the middle. All right, so we've got a 12 voltage source here. All right, we've got a 2 ohm, a 3 ohm, and a 4 ohm. And we said the current going through the whole thing, 1.33 amps, okay? So that voltage drop off, okay? So essentially, as that current moves from here to here, we're going to have a change. We're going to have a change in potential difference. There's a certain change in voltage that's occurring as the current moves through here. Okay, just like there's a certain change of voltage that moves through here, and there's a certain change in voltage that occurs through here. One thing, you know, electrical engineers, anybody that's doing anything with circuitry, electricians, you know, they're probably going to need to know what's the voltage drop off as it moves through each resistor, because the current's unchanging at this point. Doesn't matter what the resistance is, it's going to have a current of 1.33 amps. So now the question might be, well, how do I calculate that drop in voltage? Well, we already kind of have a tool to do that. So if the current was equal to the voltage over, I'll even say it's like voltage total over equivalent resistance, the I is going to be the same for all of them. So if I call this one like resistor 1, resistor 2, and resistor 3, the current's going to be the same, okay? If I want to know what's the voltage, what's the change in voltage for the first resistor, really, you know, if I just look at kind of Ohm's law, if I just do this quick, I equals V over R. You know, if I want to know the voltage drop off, I just solve for V. V equals I times R, okay? So the drop off for voltage for resistor 1 is just going to be equal to the current, 1.3, actually, let me back up. One more. Nope. Go forward. Okay. Eraser. Get rid of that real quick. Okay. Back on track now. All right. So really the voltage drop off is just going to be equal to the current times whatever resistor we're talking about. So if I want to talk about the voltage drop off for resistance 1, it's going to be the current. Oh, just making mistakes today. All right. 1.33 amps times resistor 1 in this case, which is 2 ohms. And that should get me 2.66 volts. All right. So the voltage difference from before the resistor to after the resistor is going to be a difference of 2.66 volts. Okay. So then if I go through and I want to figure out what's the voltage drop off as the current moves across resistor 2, current's the same, 1.33 amps. This time my resistance was 3 ohms. And that should get me 3.99 volts, right? We're doing good. So now I've got the last one here, you know, the voltage drop off for that biggest resistor, which was 4 ohms, so 1.33 amps times 4 ohms. this math. Let me just take a quick look. I'm going to guess 5.32, but let me double check. So I've got 1.33 times 4, 5.32. All right, that's not too bad. All right, so really what we're going to see is the voltage drop-offs for each of these resistors is, you know, some of this is really intuitive. The smallest resistor, so the thing that resists that current the most, or the least, I should say, the resistor that resists the current the least has the lowest voltage drop off. That just makes sense. One of the big things that we're going to see here is if I'm looking at the voltage total, let's just add these up real quick. 2.6666 plus 3.99 plus 5.32 equals 11.97. This is the one time I am going to start looking at, sig figs. 11.97, that's pretty close, considering we had to round the current, it should be 1.33333333, which affected my rounding here. Really, that's close enough. We could call that 12 volts, which we should see that after we figure out the voltage drop-offs, when you add them all together, it should equal your voltage source, the one that you started with in the diagram. That's just one way that you can check to make sure that you did your voltage drop-offs correctly. And remember, so going back through this, the key to remember about all of these is, second thing you might want to need, the voltage drop-off for a series circuit. Voltage drop-off. All right, so if you want to pause that, just make sure you get that written down. That's probably a good idea. But here's the big takeaway. Why do we see this voltage drop off? Like essentially, the voltage across each resistor is different because the current's the same. And really that just comes down to, so I go back to Ohm's law, I equals V over R. Really, if I solve for V, the voltage is I times R. Each resistor has a different resistance. So that means the voltage drop off is going to be different for each one. So once again, I cannot repeat this enough. The current in a series circuit is the same for all resistors. Okay, this point right here is super important when we're talking about series circuits. Anyway, I think I'm done rambling. That's enough to get you guys going. Good luck.